Hello, everyone. Today, I will be presenting my survey on metric learning and deep extensions. It's a topic central to statistical pattern recognition. My name is Li Ming, and in this talk, I will discuss the fundamental principle of metric learning, its evolution into deep learning methods, key advancements, and its real-world applications. So what exactly is metric learning? In simple terms, it's a technique that helps computer to measure the similarity in a smarter way. For example, if we want a machine to recognize faces, we don't just compare the pixel values. Instead, we want it to understand what makes two faces similar. Things like eye shape, nose structure, and facial proportions. Metric learning is useful in many areas. For example, in image search, it can help to find the similar looking images. In the text retrieval, it helps Google understand which articles are relevant. In medical diagnosis, it helps doctor to compare the patient data and find the similar cases. So instead of relying on a fixed formula, the metric learning allows the computer to learn what similarity means based on the real data. Now, why do we need metric learning? Can we just use the regular distance measurements like the Euclidean or cosine similarity? The problem is that traditional distance formulas treat all features equally, but in the real time, in the real life, some features are more important than others. For example, when comparing the cars, we might care more about the brand and engine type rather than the color. Similarity in the face recognition, the eye shape matters more than the hair color. So metric learning helps by learning which feature matter most for a specific task, which makes the similarity measurements much more reliable. So how does the metric learning actually work? One of the earliest methods in the metric learning is the Mahalanobis distance. Unlike the regular Euclidean distance, which treats all the directions the same, Mahalanobis distance adapts to the data structure. It does this by applying a transformation matrix M, which stretches or shrinks the space in different directions. So this helps to highlight important features and ignore the less useful ones. For example, in a face recognition system, Mahalanobis distance can give more weight to eye shape and less weight to background lightening. This will make it more accurate than the simple Euclidean distance. At its core, the metric learning transforms the data into a new space where similar things are closer together and the different things are farther apart. After the transformation, we can use a simple Euclidean distance to measure the similarity. So imagine a data set of handwritten numbers. Before the metric learning, the numbers might be scattered randomly. After the metric learning, all the threes are grouped together, all the eights are grouped together, and so on. This makes the classification much easier. A common way to do this is by learning a transformation function L, which will map the data into a new space. Early metric learning methods like Mahalanobis distance work well, but they are limited to the linear transformations. With the rise of deep learning, we now have deep metric learning, which learns both the features and the similarity functions at the same time. This is especially useful for images, text, and speech, where the similarity is complex and it's not just a simple mathematical formula. Deep metric learning allows the models to learn high-level patterns that classical methods struggle to capture. Now, let me briefly run through the three classic methods in the metric learning. The first one is called large margin nearest neighbor. We call it LMN. So it employs the margin-based constraint to align the local neighborhoods, which can ensure the same class points could stay close, while imposters are pushed away, which helps to improve the K nearest neighbor performance. And the second method is called the triplet loss. It will enforce a relative ordering among anchor, positive, negative samples to learn a discriminative embedding. The idea is simple. Add a margin to make anchor be closer to the positive than to the negative. It is very common in the face recognition. The third one is called constructive loss. It applies the pairwise constraints. This method compares pairs of samples. So when a pair is similar, it will minimize their distance. When there are differences, it will push them apart. So it is often used in Siamese networks, which we will talk about later. So the triplet loss and the constructive loss we just mentioned are called traditional loss function. They do work well, but they have some limitations. To improve the training efficiencies, newer methods have been deployed. Multi-similarity loss, for example, it will look at the multiple similarity factors to improve the learning. And the proxy neighborhood component analysis loss, it will use the class representative instead of comparing the individual pairs, which will speed up the training process for a lot. The third one is called quadruplet loss. It will introduce an extra negative example to make the model even more precise. So this improvements will help the metric learning models train faster and perform better, especially in the larger data sets. Next, let's zoom out looking at this overview table. This table sums up over 50 methods and sorts them by how they are supervised, whether they are linear or nonlinear, how well they scale, and even extra features like dimensionality reduction or spatial regularizers. It will give you a big picture of the whole field and also showing how this classic methods we just talked about it to fit it into a broader landscape and how the newer methods build on these core ideas. One of the biggest challenges in the metric learning is choosing the right examples to train the model. If we pick the random pairs, most of them will be too easy, and the model won't learn too much. Instead, if we use a technique called hard negative mining, which selects more challenging examples. So let's see, there are 3 levels of negatives. The first level is called random negatives. So these are often too easy and don't help learning. There's a second tier called the hard negatives. These are the incorrect, but they are very similar to the correct answer. By training with this, we can force the model to improve. And the last one is called semi-hard negatives. So these are not the hardest cases, but they are still challenging enough to be useful. By focusing on the harder examples, we will let the model to learn faster and generalize better. Moving on to the real-world impact, when we use these learned metrics, performance measures have significant boosts. In this face recognition case, methods use continuous label to learn richer similarity information. By preserving the distance ratios in the new triplet loss and adapting triplet mining, which leads to significantly improved in various image retrieval tasks. On the top picture, we can see each image is labeled by a human pose with the same person. and colored in red, which means the pose similarities to the pose similarity to the anchor is very high. In the part B, the actual dotted lines show how the distance got changed during the training process compared to the ideal cleaner separation in the part A, enhancing both classification and retrieval. It will for sure will allow the distance ratio in the label space to be preserved in the learned metric space so as to overcome the limitation. So where is the metric learning actually used? The first case, face recognition. Algorithms like FaceNet and ArcFace are very famous, and they learn embeddings that to distinguish the faces more accurately. The second example is image retrieval. Google's visual search used the metric learning to find similar images. And also for the cross-model retrieval, OpenAI's CLIP model aligns the text and image embeddings so we can retrieve the images using the text descriptions. No need to mention the healthcare and the music recommendations are also very common in our daily life. Let me give you another example. Let's look at how a Siamese network. On the left, you see our ideal scenario, right? So same class images are grouped and different class images are far apart. This confirms the Siamese network's core idea. By comparing the image pairs with an appropriate loss, it will learn an effective metric that improves task, for example, the digit recognition. On the right, as training goes on, the blue line, which represented dissimilar images, will go up, while the orange represent the similar images will drop. This evolution clearly shows that the network is learning to capture the true symmetric relationships, exactly what we want in metric learning. Despite its success, metric learning still faces key challenges. The one major issue is fairness and bias. Some models work better for certain groups, particularly in face recognition, raising the ethical concerns. Researchers are working on ways to reduce the bias and improve the fairness. Another challenge is scalability. As the datasets grow, the training models effectively becomes more difficult. Optimizing the computational and using the technique like low rank approximation can help. Also, the self-supervised learning is another major research area. Since the metric learning relies heavily on the label data, the question is, can we train the models effectively without it? New methods like the constructive learning are promising that. Finally, continual learning is a challenge. Most models don't handle new categories well without forgetting past knowledge. Finding ways to update models without retraining from scratch is an ongoing research problem. Overall, solving these challenges will be key to make the metric learning more accurate, fair, and scalable. To address these challenges, researchers are exploring several directions. One is end-to-end deep metric learning, where models learn both feature extraction and similarity measurements simultaneously, improving their efficiency. Another is multitask learning, allowing one model to handle multiple tasks, like face recognition in different lighting conditions or object detections in images and videos. For scalability, new techniques focus on faster training and reduced computation, using the sparse representations and improved optimization methods. Finally, self-supervised learning is gaining attention using unlabeled data and constructive learning to train the models more effectively. So this advancement will make the metric learning more powerful and adaptable across the various fields. That includes all my presentations. Thank you for your time, and I look forward to your questions. Bye-bye.